Welcome back, everyone. I am incredibly excited to guide you through today's explainer. We're looking at a truly fascinating new research paper called SEAL, Synergistic Co-Evolution of Agents and Learning Environments. This was put together by Yihao Hu and a frankly brilliant research team. If you've been following the rapid advancements in LLMs lately, you already know that training them to interact with the world and actually use digital tools is the absolute bleeding edge of AI right now. But there's been this hidden ceiling kind of holding these agents back. So today, we're going to set the stage for how we currently train these models, and more importantly, how this brand new framework completely shatters that ceiling. Get ready, because the way we teach AI is about to fundamentally change.
Okay, let's dive right into this. I want you to imagine, just for a second, being a rapidly advancing brilliant student. You're mastering complex equations, you're reading advanced literature, and your brain is just an absolute sponge. But you're permanently stuck in a static classroom. The teacher only ever hands you the exact same, outdated textbook day after day. You're evolving sharp, but your environment isn't giving you the feedback or the new challenges you actually need to reach that next level. You'd hit a wall, right? Well, according to the researchers behind this paper, this frustrating scenario is exactly what's happening right now to our most advanced AI agents.
So the researchers actually coined a specific term for this roadblock, and it's really the core problem driving this entire paper: Agent-Environment Misalignment. Think of it as a structural gap in how we currently build self-evolving AI. You see, as an LLM agent practices and improves through interaction, its capability frontier actually changes. It learns new things. But the learning environment itself, the system that oversees it, corrects it, and provides supervision, well, that remains completely static. It's only weakly coupled to the actual specific failures the agent is experiencing. The model is essentially adapting in total isolation, trying to learn from a rigid world that doesn't adapt back.
To solve this massive bottleneck, the researchers introduced what I like to call the symbiotic fix. They call it SEAL. That stands for the Synergistic Co-Evolution of Agents and Learning Environments. Basically, it's a closed-loop framework specifically designed for interactive tool-use agents. You know, these are the AI models we ask to go out, use software, search the web, and solve complex, multi-step problems. Instead of leaving the agent to figure things out in a rigid box, SEAL transforms the whole training process into a dynamic two-way street.
And this brilliantly illustrates just how stark this paradigm shift really is. The old way is isolated adaptation, meaning either the agent's policy adapts or maybe someone tweaks the environment, but they do it totally alone. SEAL's approach, though, is synergistic coevolution. Under this new framework, both the agent and the environment evolve together, simultaneously. They're locked in this closed loop, constantly passing shared signals back and forth. When the agent fails, the environment learns how to teach better, which in turn helps the agent learn how to perform better. It's a total game changer.
So how does this actually work under the hood? Well, it breaks down into three pretty elegant steps. First, SEAL collects on-policy trajectories under executable verification. In plain English, it basically just lets the agent try to solve a problem and verifies if the actions it took actually worked. Second, when the agent inevitably messes up, SEAL diagnoses these failed rollouts and breaks them down into specific turn-level failure labels. It figures out exactly where and why the agent tripped up. And third, and this is the absolute magic step, it takes those specific diagnoses and uses them as a shared signal. Just like a great teacher and a student sitting down to look at a failed math test together, both sides use that exact same mistake to improve.
Let's look at what actually happens to the classroom in this scenario. How does the environment adapt based on those failure signals? According to the paper, it evolves its learning interface in three really key ways. First, it exposes clearer tool affordance cues. Basically, that means giving the agent way better hints about what a specific tool can and cannot do. Second, it provides critical constraint information, making the actual rules of the task much clearer. And third, it offers recovery-oriented feedback. So instead of just throwing an error and saying you failed, the environment learns to provide specific feedback that guides the agent on how to recover from that specific mistake. It ensures the AI isn't just blindly guessing on its next attempt.
Let's move to the other side and see how this builds. Because while the environment is busy becoming a much better teacher, what's happening to the agent? Well, its actual policy is simultaneously being updated based on those exact same failures. The researchers call this diagnosis-guided advantage reweighting. It sounds complex, but basically, because the model and the environment are sharing the same failure diagnosis, the agent optimizes its policy to specifically target and correct its weakest points, taking full advantage of this newly adapted, highly informative environment. The two halves of the system are literally pulling each other upward.
Now, in the world of training large language models, we are usually talking about millions or even billions of data points, massive compute, massive resources, which makes this next number just absolutely staggering. 400. The researchers found that the SEAL framework is so incredibly efficient at identifying and correcting errors that it requires a mere 400 training samples to yield significant improvements. This isn't just a win for AI capability. It's a massive breakthrough for low-resource agent learning. It proves that you don't always need an ocean of data if your feedback loop is smart enough.
Now, what's really interesting about this is the sheer scale of the performance boost. In notoriously difficult multi-turn tool use evaluations, SEAL achieved average point gains ranging from an 8.25 all the way up to an incredible 26.25 points. Furthermore, they proved this wasn't just a fluke by testing it across 3 completely different AI model backbones. And perhaps most impressively for sure, it exhibits positive out-of-distribution transfer, meaning the agents didn't just memorize the test, they genuinely got smarter, and they could apply their new skills to entirely new, unseen problems.
The researchers capture this crucial point perfectly in their abstract. They state, these results demonstrate the value of jointly adapting the learner and its training time learning substrate for robust, self-improving LLM agents. So the big takeaway here is that you can no longer look at an AI model and its training environment as 2 separate entities. To achieve true, robust self-improvement, the mind of the AI and the world it learns in, they have to be treated as a single co-evolving package deal.
Which brings us to a rather profound question to close out our explainer today. We've just seen that by linking the agent and its environment in a closed loop, the efficiency and capability of AI spike dramatically, and with minimal data. So if AI agents and the virtual worlds they train in can now synergistically evolve together, literally feeding off of each other's improvements in real time, what actually limits how fast they can self-improve? It's a thrilling and honestly maybe a slightly daunting glimpse into the future of artificial intelligence. Thank you so much for joining me for this explainer. Keep asking questions, and I'll see you next time as we continue to decode the cutting edge.